process calculation. So in the previous lecture, I have discussed about the Buckingham pi theorem, and where we have seen that how we can reduce a large number of variables in dimensionless parameter, and then we can calculate the variation of a particular parameter based on the reduced form of dimensionless variable, right, or dimensionless number. And I have given one simple example of calculation of pressure drop or pressure drop in a circular pipe, and where we have seen that there were you know six number of variables, and total number of primary variables were 3, and then out of this we have subtracted 6 minus 3 from the Buckingham pi theorem, and we got 3. So based on this 3, we could have made 3 dimensionless parameter, pi 1, pi 2, pi 3, and then we have calculated the value of pi 1, pi 2 and pi 3. So we observed that the value of pi 1 was delta p upon rho u square. Pi 2 we got a Reynolds number, that is inertial force upon viscous force, and pi 3 is the geometrical ratio of circular pipe, that is L by D. And here you can see that we can directly see the proportionality of pressure drop at with respect to the dimensionless number, that is Reynolds number, and geometrical ratio. So I hope this is fine, but my only request would be that if you are able to solve at least 5 to 10 questions on Buckingham pi theorem, then it will strengthen your concept. So better to solve some questions, so that you will, if any question is coming in your exam, it will be easy for you to solve. So in today's lecture, I'll be talking about the fundamental concept of stoichiometry. It's very important. So when we talk about the stoichiometry, so the first I'll be talking about some foundation about this. So the stoichiometry word, that has its origin from the Greek word, that is stoichion. The meaning of stoichion is the elementary constituent. And then metrion, and the meaning of this one is to measure. This has nothing to do with your exam, but again, if you are understanding any concept on the fundamental level, you should understand the basics of that also. That's why I'm explaining all of these things. So if we talk about the conventional meaning of this word, so the conventional meaning of this word limits its application to the calculation involving the quantities of material that involve in the only chemical reaction. So but here we are dealing with the chemical engineering problem. So in chemical engineering problem, the word stoichiometry is used in a broader sense. It's not just limited to the law of combining proportion in chemical reactions. So when we talk about the chemistry, the word stoichiometry is only limited to the law of combining proportion. And these things already I have discussed in my first lecture, where I was talking about some fundamentals regarding stoichiometry and process calculation. But in broader perspective, if you see the meaning of this stoichiometry word in the chemical engineering, so for chemical engineering, if I say where you will be dealing with a problem in the large scale industry, so this particular word is having a broader meaning. So you will be dealing with the calculation that will be involving your behavior of gases, and we will be understanding all these things in the subsequent lecture. Gas mixture, because you actually deal with the real problem in the industry, right? Phase behavior of liquid, liquid solution, that basically we study in thermodynamics topic, right? And the material and energy balance in unit operation. and many more problems will be there, right? So so you would have seen that in chemistry, basically, if you have a reaction, and then with respect to the reaction, if you observe the reaction and you see the stoichiometric coefficient, and you directly tell, let's say, if 2 moles of A plus 3 moles of B is converting into 5 moles of C, so directly you can say, while observing the stoichiometry, that 2 moles of A will form 5 moles of C, or 3 moles of B will form 5 moles of C. So the application of this stoichiometry is limited up to this particular principal component or law of combining proportion in chemistry. But when we talk about the chemical engineering, it is having a broader meaning, like behavior of gases. That gas can be ideal gas or real gas mixture. We also study the phase behavior of ideal solution or real solution or liquid solution. We perform the energy and material balance in the real industry, problem in the real problem in the industry. So that's why you can see that this particular concept becomes very, very important for the chemical engineers, right? Now, going deeper into this particular concept, I'll be talking some fundamentals regarding the stoichiometry here, where I'll be talking about some mole concept thing, right? So if I want to, so I'll start with the mole concept here. I'm not going to define the mole and all these atom molecules. You would be knowing all of these things here. But when I talk about the number of moles, moles can be defined as mass of a substance in gram and divided by your molecular mass. Right, mass of a substance in gram divided by molecular mass. Or you can also define the value of kilomole, because we will be frequently dealing with the mole and kilomole thing in our real problem. So you can write also here mass in kilogram divided by molecular mass, right? Mass in kilogram divided by molecular mass. Or sometimes also you have to use the lb moles. That will be equals to mass in lb and divided by molecular mass. So already I have discussed how to convert your kg into lb, all these things in my first lecture or second lecture. If you go there, then definitely you will be able to understand the conversion thing, right? So that's why I told you conversion is very, very important when we are talking about the problem in the real world industry, right? So here I'll be taking a very simple example to let you understand how do we calculate the molecules or number of moles, right? That is not required here, but because this course I have designed for the fundamentals thing, so that students in the semester first can understand this subject. So that's why I'll be solving some fundamental problem also. So let's take one example, that how many molecules are present in 690 gram of K2CO3. So here this is a potassium carbonate, and we are trying to find out the number of molecules present in 691 kilograms. So when I talk about the molecular weight of potassium, so sorry, atomic weight of potassium, this is yours 39.1 gram per mole, right? The unit will be gram per mole. Carbon, the mole, this will be gram per mole, and for oxygen it is your 16 gram per mole. So you would be knowing these things. So first we have to calculate the molecular weight of K2CO3. So that you would be knowing, that is 2 into 39.1 plus carbon is 12 plus 3 into 16. So if you perform this calculation, you will be getting the value of 138.2 gram per mole. Is that clear? So now you have molecular weight in your head. Now you can calculate the number of moles, right? Number of moles will be, I have told you, that weight divided by molecular mass. So weight has been given to you in the problem, that is your 691 gram, and this is given as 138.2 gram per mole. Is that clear? I hope this is clear to all of you. So once you calculate these things, you will be getting approximately 5 mole. right? So you have 5 moles of K2CO3, right? So in 1 mole, basically in 1 mole, any molecules or any atom contains 6.023 into 10 to the power 23 molecules, right? So we have 5 mole, right? In 5 moles it will contain 5 multiplied with 6.023 into 10 to the power 23 molecules. So basically if you will calculate these things, it will be equals to 30.115 into 10 to the power 23 molecules, right? So this is very simple problem that you can solve. But again, why I'm telling you to solve all these simple problem, because sometimes you get stuck while solving, because you, if you focus on the advanced concept only, and if you are not able to revise the fundamental thing, then somewhere eventually if it is coming in the problem, you will get stuck. That's why all of these kind of problems are very, very important to solve, right? Now, moving towards the next concept of this particular problem, I'm not solving many question on that calculation of number of moles. This is very fundamental concept in chemistry, you would be knowing. So next I will be talking about chemical calculations and use of molar quantities, right? It's very important to understand, because when we will be talking about the recycle, bypass and purge, there also there will be some kind of reaction that will come. So before that you need to clear with all of these concepts, then only you will be able to understand some reaction involving recycle, bypass and purge, right? So just try to understand this thing. So when we talk about the conventional application of stoichiochemistry, so it is concerned with the mass mass relation that involves in the chemical reaction, between the reactant on the one hand to the product on the other hand side. But the mole concept is found to be very helpful in dealing with calculation that involves in chemical reaction, that compared to those using ordinary mass unit. So if we talk about why basically we are going to study this concept, the application of this particular concept is very important, because right now we have seen that, okay, we have a specific amount of K2CO3 was there, and we have calculated the number of molecules, right? Here no reaction was happening. But when there is a reaction, if the reaction is happening, and if you want to calculate how much amount of product that is being formed with respect to a particular amount of reactant, then how will we calculate these things? And that is where the chemical calculation that requires molar quantities becomes very, very important. So let's try to understand one thing. So let's say you have I'll tell you these things with the help of one example here. So let's say you have a iron pyrite FeS2, right? And it is getting oxidized, and it is forming your iron oxide Fe2O3 plus sulfur trioxide, right? So if you do the balancing of this reaction, you must be knowing all of these things. I am directly balancing this, and you can balance by the method, right? So now this is a balanced chemical reaction. So whenever you see any chemical reaction, first try to balance that. Now here if I am asking how many kilogram of pyrite are burned to obtain 100 kg of sulfur trioxide. This is very simple question, but again, as a chemical engineer, let's say if you are working in the iron industry, then you'll have to deal with all of these kind of reactions as well. So the important thing here is that you have to see the reaction first. So this is a pyrite, you must be knowing, and this is your sulfur trioxide SO3. So they are asking how many gram of pyrite are burned to obtain 100 kg of SO3. So SO3 is getting formed is 100 kg here, and how much FeS2 is FeS2 copper pyrite are required. So if you see here again, I'll write a reaction, this reaction 4 FeS2 plus 15O2, that will give you 2 Fe2O3 plus 8SO3. So from this particular chemical reaction we can say that 4 moles of FeS2 will give you 8 moles of SO3, right? So if you have 100 kg of SO3, so better to convert this into mole. That will be easy. So first you have to calculate the molecular weight of SO3. Is that clear? And what will be the molecular weight of SO3? That is your 32.06 plus 3 into 16. That will give you 80.06 gram per mole. Right. Now you have the molecular weight. Now I'll calculate number of moles of SO3, that is 100, it is in kg, multiplied with 100 gram and then divided by 80.06 gram per mole. So now you will be getting the value in the moles. So if you see here, the value you will be getting is 1.249 into 10 to the power 3 moles, right? Now you have this value of moles, but from the reaction what you see that 8 moles of SO3 is getting formed using 4 moles of FeS2, right? So we can write 8 moles of SO3 is being formed by how much? 4 moles of FeS2. 4 moles of FeS2. So for 1 moles of SO3 will be formed by 4 by 8 moles of FeS2, and you are supposed to form how much? 1.249. So 1.249 into 10 to the power 3 moles of FeS2 will be formed by 4 by 8 into 1.249 into 10 to the power 3. So once you perform this calculation, right, so you will be getting how much? 0.624 into 10 to the power 3 moles. Now you have this moles of FeS2, so you have 0.624 into 10 to the power 3 moles of FeS2, but they are asking you to calculate how much kg of pyrite required. So for these things you have to calculate again molecular weight of FeS2, and molecular weight of FeS2 you can calculate it very easily. You will be knowing the atomic weight of iron as well, plus 2 into 32.06. So that will give you 119.97 gram per mole. Now you have that mole and you have this one. So you have mole and this thing. So now you can calculate what is weight of FeS2, that is your moles into molecular weight, right? Moles into molecular weight. You know the moles, 0.624 into 10 to the power 10 to the power 3 and multiply with molecular weight 119.97 gram per mole. So these moles will get cancelled out, and finally you will be getting the value of if you do the calculation, you will be getting the value of 37.48 kg approximately, right? So now you would have understood that how this chemical reaction becomes very important to calculate the amount of reactant that is required to produce a fixed amount of product. And where stoichiometry came here, because this is the stoichiometric coefficient of the reactant here, 4, and the stoichiometric coefficient of product here, which is in the yellow circle, right? So now you would have understood the importance of these things, because the reaction that is happening here, you have to use the law of these things. How, based on the stoichiometry only you can deal with that. So that's why here I have written 8 moles of SO3 is being produced by 4 moles of FeS2, and we are writing these things because of this stoichiometric coefficient of this chemical reaction. So I hope you would have understood why this stoichiometric things are very important to understand, right? So similar kind of reactions that you can also write, that I'm not going to write here, right? So this is about calculation of moles, right? Now further we'll be moving towards the calculation of the equivalent weight, right? So like how we calculated number of moles, it was like weight divided by molecular weight, right? This was the weight divided by molecular weight. Is that clear? But if I want to calculate number of gram equivalent, that will be your weight divided by equivalent weight, right? It's very important to understand. We'll tell you why this is important when we deal with these kind of reactions. So because let's say if some reaction that involves transfer of charges, right? So if charges are not involved, then definitely you don't require this kind of equivalent weight concept. You can deal all of these reactions in the number of moles. But when we talk about like redox reactions, right? So in let's say if you are dealing with some electrochemical reactions, that is a redox reactions, and there you require some amount of charge because that reaction is happening due to the charge transfer also. So there you require this kind of equivalent weight concept, right? Or gram equivalent. I'll tell you in the next case. So then the most important thing is how to calculate this equivalent weight, right? So to calculate this equivalent weight, so we can write molecular weight multiplied with n factor, right? Molecular weight multiplied with n factor. So sometimes n factor is also called as valency factor. N factor is also called as the valency factor. Okay, so now let's try to understand how we can calculate the valency factor. So let's say for charge species, right? So let's say if I'm talking about what is the equivalent weight of sodium plus, right? So equivalent weight of sodium plus will be what? So first we have to calculate the valency factor or n factor. So for sodium, n factor will be 1. Why? Because what would be the positive charge over there? So that is equals to number of charges. Okay. Or if I am talking about Mg2 plus, so for Mg2 plus, what will be the n factor? That will be 2. If I am talking about Al3 plus, what will be n factor? That will be 3. Is that clear? Right. So let's say if I have to calculate n factor for Cl minus, right? So n factor will be 1. So basically what we are doing, we have to write whatever the amount of charge that is being involved over there, in the reaction. That's why we have to calculate the n factor or valency factor for that. Now this is your n factor for all the charge species. Is that clear? Now coming to equivalent weight. As I have told you, that is equals to n factor multiplied with molecular weight. Is that clear? So let's say for Na plus, what will be the equivalent weight? Equivalent weight will be equals to 1 into molecular weight, right? So 1 into molecular weight, that's it. For let's say Al3 plus, what will be the equivalent weight? Sorry, this is equivalent weight. N factor, that is 3 into molecular weight, right? So and so forth, you can calculate all of these things, okay? Or what would be the equivalent weight of let's say Na2CO3, Na2CO3, sodium carbonate. So now first you have to break this particular thing is 2 Na plus and CO3 2 minus, right? So if you see here, there are two positive charge, 2 plus and 2 minus, that is involved. So you have to take the valency factor here 2, right? Or if I am talking about MgCO3, so if I break MgCO3 into Mg2 plus and CO3 2 minus, so here you can see that your valency factor, that will be equals to 2, and then we can calculate right. So you must be knowing the no sorry, it is a and my equivalent weight is equals to molecular weight divided by n factor. I am sorry for that, right? Divided by n factor. So basically you have to divide here, sorry for that, by 1, right? Here you have to divide by molecular weight by 3, so and so forth. So now if I talk about equivalent weight of let's say MgCO3, I can write molecular weight of MgCO3 divided by valency factor is 2, right? If I want to find out equivalent weight of HCl, I have to break this into H plus or Cl minus, right? So what will be the equivalent weight of, that is equals to, you will write molecular weight divided by 1, because here valency factor or n factor will be equals to 1. So similarly you can calculate all of these things. It's not very big deal, but yes, you have to understand how we have to calculate the n factor or valency factor, and then we should proceed with that, okay? So we get to know about the equivalent weight concept and molecular weight concept. So now next I'll be moving towards the composition of solid, liquid and gases. This is very important because you will be dealing with all of these kind of problems. So composition of solid, liquid and gases, and here I'll be talking about some fundamental concept, that is your mass fraction first. So I'll be talking about the concentration term for all. Right. This is also called as the weight fraction. So just don't get confused about that. So if I have mixture of two solids, let's say, or binary solids, and we want to calculate the mass fraction of two components. So let's say we have different solids, this blue one, and then there is a red one. So if I'm talking, there is B and blue one is your A. So if there will be some mass of A involved, right, that is your A, Ma, and mass of B involved is your Mb. And if I want to calculate a small Wa, that is your weight fraction of A, I can write Ma divided by Ma plus Mb. Is that clear? If I want to write Wb, a small Wb, that is your weight fraction of V, I can say that Mb divided by Ma plus Mb. Is that clear? So the meaning of these things is, if I want to calculate weight fraction of any component in a multi-component mixture, so I can say that mass of that particular substance divided by summation of I equals to 1 is to n, and then that will be Mi. Is that clear? Okay. So this was in terms of mass fraction, right? Then if I talk about second parameters, that is your weight percent. Similarly, I can define, so let's say if you have a mixture of two and more than two solids, or so there is B and there is A, and you have your Ma and Mb, and if I want to calculate weight percent of A, right, I can say that, sorry, here, weight percent of A, that is equals to Ma divided by Ma plus Mb into 100%, that will be with the percentage, right? I can also say weight percent of B, that will be equals to Mb divided by Ma plus Mb into 100%. Is that clear? So this is how you can calculate the mass percent and weight percent, right? So with that, I would like to end this lecture here only today, and in the next subsequent lecture, I will be talking about the mass ratio and the calculation based on the dry basis and weight basis, and then I will be talking about some concentration term that is very important to understand also, and then we'll move towards some reaction involving some physical process and all. So this becomes very important. Okay, thank you all for attending this lecture, and stay tuned with this lecture. Thank you.